Okay, so let's use Stokes' theorem to do this example. So h is the top half of the sphere of radius 3. We have this vector field. We want to compute the surface integral of the curl of f over that vector field. Well, we're just going to use the Stokes' theorem here. So let me try to sketch this, because the tricky part about Stokes' theorem is that we're going to have to figure out what the orientation on the boundary should be. So this is like a quarter of this circle, because I can't really draw the rest of it. Okay, the back of it is like this, but this is a circle, or this is a sphere, and we want the top half of it. Now I didn't say it, but we want the outward pointing orientation for this sphere. So when we talk about this, we mean the sphere with outward pointing orientation. Okay, so the boundary curve is going to be just the curve then x squared plus y squared is equal to 9. And now we need to determine whether we give this the counterclockwise orientation or the clockwise orientation. And we're just going to do the thing that I mentioned before. So if you walk along the boundary of the curve with your head pointing in the direction of the normal vector, your head is going to be pointing like that way. Okay, so if you walk around in the clockwise direction with your left arm sticking out, then your left arm is going to be pointing down away from this hemisphere. But if you walk around in the counterclockwise direction with your left arm sticking up, then you're going to be walking. Then you're going to be walking with your left arm over the hemisphere. So the orientation. So if the surface has outward orientation, this induces a counterclockwise orientation on the boundary. So then what we want to compute then, the thing that we want to compute is the line integral of that vector field over the circle of radius 3 centered at the origin with counterclockwise orientation. So the parameterization of that, so to compute this, we need to come up with a parameterization. The parameterization, we'll just use the standard one. This is 3 cosine t, 3 sine t, 0 less than or equal to t, and we're just, less than or equal to 2 pi. Don't make the mistake I did. We're only going over the hemisphere, but the boundary circle is a whole circle. So t does go from 0 to 2 pi. And so this means r prime of t is equal to minus 3 sine t, 3 cosine t. And so the vector field integral, or the t integral that is equal to the vector field of the line integral of the vector field is the integral from t is equal to 0 to 2 pi. The vector field is f, so y is 3 cosine t. So this is going to be 3 cosine t. Y is minus, I got that wrong. Why did I say that? Y is 3 sine t. So this is 3 sine t. Then minus x, that's going to be minus 3 cosine t. And then minus x squared minus y squared. Well, that's just going to be equal to minus 9. Okay, because x squared is 9 cosine squared. Y squared is 9 sine squared, so yeah, that's equal to minus 9. And now we're going to dot this with, so notice up here, I foolishly left off the third component, but notice that the third component is always going to be equal to 0. That's the z component. Z is always equal to 0. So this is, z is always equal to 0 for this curve. So then this is going to be minus 3 sine t, 3 cosine t, 0 dt. And now this is just a t integral. And so what it becomes, if you look at it, this is going to be, I'm going to erase this part for the next video, but I'll write it here. This is the integral t is equal to 0 to 2 pi. 3 sine t times minus 3 sine t, that's minus 3 sine squared. Then it's going to be minus 3 cosine times 3 cosine, that's minus 3 cosine squared. And so again, this just ends up being minus 9 dt. And so this is equal to minus 27 pi. Well, it's not equal to minus 27 pi. I don't know why I said it was equal to minus 27 pi, but it's too late to change the video now. It's minus 18 pi because 2 times 9 is 18, not 27.